Well, so the first long part of the lecture, I've been introducing the framework and giving you some technical details, but not too many. Now I go on with some examples, which I hope will give you a better feeling of how we can use these models to solve some pattern recognition or learning problems, and also how to investigate partially how these models work internally, how we can explore, for example, the internal representations, the features extracted by these unsupervised learning models. And I will mostly give you examples from my own research, so cognitive neuroscience research, and briefly mention them, some examples from network optimization. I will also introduce the problem of learning sequences, because up to now we are only discussing learning static input patterns, like images, like vectors. But what if we have a series of images, like a movie, or a series of speech streams, for example? Okay. How can we model them in an unsupervised way? That's also quite challenging. But first, let's see a prototypical problem, which is that of recognizing handwritten digits. This is the standard benchmark that was used until 15 years ago in the machine learning community. Now they are using much more challenging benchmarks. But this is still very useful to get a general feeling of how a neural network can work. So the MNIST dataset is composed by 60,000 little images, 28 by 28 pixels, that many different peoples have been writing, okay? So I remember somewhere, Ian LeCun or Jeff Hinton, they were paying beers to people for writing these little images back in the 80s, 90s, to collect this huge amount of data that could be used then for training neural networks. So we have many little images with digits inside, and we can train a neural network like this. So 784 is the size of the visible layer. Why 784? Because we have 28 by 28 matrices, okay? We can just take a matrix and linearize it, vectorize it, right? So we can use vectors rather than bidimensional matrices, but the idea is completely the same. Then we have a first restricted Boltzmann machine with 500 hidden neurons. We train it, and then we freeze these connection weights, and we go to the next restricted Boltzmann machine, other 500 neurons here, and then we stack the last and the larger Boltzmann machine with 2,000 hidden neurons. You see that there are only bidirectional connections, so this is completely unsupervised. There's no classification task here. So with a supervised feed-forward neural network, you would have also an output layer here representing the digit class. Like this is class 7, so I activate the neuron corresponding to the digit 7. Here we don't. Here is completely unsupervised. We are just trying to reconstruct the input or the hidden activations in order to build a hierarchical generative model of the data distribution, okay? Once we've learned the connection weights, we can ask, okay, but which type of features is the network learning? In order to do this, we can investigate the so-called receptive fields of the hidden neurons. A receptive field is like the portion of the visual input or the type of visual input that is preferred for a neuron. How can we look at the receptive field, for example, of this hidden neuron? Well, we just take its connection matrix, okay, with all the visible units, and we put it again into a bidimensional matrix. So this is the original topology of the input. And then we plot the strength of the connection, of each connection, using a color scale, for example, a gray scale. So in this case, if a connection is close to 0, it will be gray. If it is very strong, it's becoming white. And if it is very negative, strong but negative, it's becoming black, okay? Before learning, the receptive field of this neuron will be likely random, like this. You see, random and close to 0, because usually these networks are initialized with small random ways, close to 0. But after learning, maybe the neuron is becoming location specific. You see, this is like a filter which is detecting an edge. Okay? It is like similar to a Gabor filter some way. So we have all connections after learning are becoming 0, apart for these connections. Some of them are strong inhibitory, negative. Some of them are strong positive, excitatory. And this type of feature can be useful, for example, for describing the lower part of this figure, for detecting the border, which is describing the digit 7, okay? So this is a useful feature to describe the input data. So if we look at the receptive fields of these neurons, what we see, it's interesting. At the first hidden layer, the receptive fields are like this. They look like Gaussian blobs, or what in neuroscience is called on-center, off-center detectors. These are the receptive fields that usually are observed in the retina or in the lateral geniculate nucleus of the thalamus. Let me go back a few slides here. Okay. Early visual stages. The retina and the thalamus perform this basic visual filtering. Okay. So this neuron, for example, will only fire when there is something inside this point in the original image, okay? So probably in this case, this neuron will fire because the 7 digit is indeed including something here. But maybe there are another neuron, maybe this one, which is firing only when there is something up here. In this case, there is nothing, so this neuron will not fire, okay? So these are the features that are being extracted by this first hidden layer. The second hidden layer, here the neurons learn to combine these basic features in order to discover something slightly more complex. For example, edges. You see, these are now Gabor filters or edge detectors like this one, okay? So these neurons are firing only when there is some elongated edge into their receptive field, okay? And up to the third hidden layer, where the features are becoming even more complex, like this. So I should say that now I also included in this network a sparsity constraint. I don't have time to discuss it in detail, but basically I'm asking all the neurons to be as independent from the others as possible in this way. And you see, for example, that some neurons are learning to represent whole digits. So this neuron probably will only fire when the number 9 digit is presented here, which is, I think, pretty amazing because it is completely unsupervised. Let me say it again. There is no supervised task here. We are not asking the network to classify the digits or to discover that 0 is different from 9. This is supervised. We are just asking the network to describe the input distribution. But still, the network is discovering these abstract classes. The network thinks that the number 3 is something that should be represented in the high-level representation, separately from number 4, from number 8, from number 1. So it's like if it is performing a high-level clustering, which is disentangling the representations and making each digit having a representation which is different from the other digits, okay? So this is why we say that high-level representations can emerge also from unsupervised deep learning. You don't need to provide labels or explicit supervision. What can we do once that we have these high-level representations? We can read out them. We can perform supervised tasks. So maybe we still want to classify the original input images, but rather than classifying here directly on the images, or here, we may try to perform classification from this representation, which is more complex. It's like if we have a feature space provided by a kernel function, which is more informative, is making features more explicit, okay? We can even try to perform linear readouts, okay? Just putting straight edges between the classes. If we perform the readout here at the input images, classification is 86% of accuracy. But as we move up in the hierarchy, we might reach up to, for example, 96, 97%. So the higher we go in the hierarchy, the more separable the classes are becoming. Even if, let me say once again, learning is completely unsupervised. The goal was not to classify. The goal was just to build representations, to discover features, to discover regularities. Then after we built good representations, we can perform a linear readout. Okay, we can train a linear classifier. And the classifier will likely benefit a lot. So if you try to train the classifier directly here, it's going to be hard to separate the classes. But on the top layer representations, it's going to be pretty easy to separate the classes. Okay. What we can do, and this is interesting also for simulating top-down effects, is we can generate sensory input. Because these are generative models. These are bidirectional connections. So we can start from the top level representation and go down and try to generate inputs in the retina, in the sensory dimension. Okay? So in this demo that I'm going to show you, we have an additional layer here, which is like a bit tricky. The architecture is exactly the same that we have here. So we have an input images of digits. We have 3 layers of unsupervised discovery of representations. But then we also stack some supervised information in the last deepest layer. Okay? So this is the 2000 units layer, and we jointly train this Boltzmann machine by also adding some label information in the visible layer. Okay, so this is the whole visible layer. Okay, these are the hidden units. We take in the visible layer both the hidden representation coming from the sensory image, but also a class label which is representing the underlying class. It will be clear now when I show you the demo. Okay, so we have a real-time representation of the neural network here. We have the input layer here, 2 hidden layers, the top hidden layer, and as I said, here as input we also provide information about the class. Okay, so it's like a supervision signal now. We have, for example, this is active only when the 0 input is presented. So if I give you number 0, okay, now I can process this pattern and ask to estimate which is the underlying class by updating the activations of the network. You see, at first it was a bit uncertain, but now is reliably classifying it as being of class 0. Okay, so correct classification. Sometimes it's changing, then it goes back to 0. Sometimes it's getting confused, for example, by 8, 6, which are patterns that share some features with the class 0. Okay. What you can see is also that the activation is always changing because it's a stochastic network. So the activations are always probabilistic, are changing every time. We can speed up, and you will see that at the end, it's pretty stable. It's classifying always correctly the digit to the 0 class. I can change and provide an input of class, this one. An input of class 6. I do the same. You see the network is classifying it as being of class 6, which is represented by this neuron. Okay. Let me try another one. Maybe the pattern 3 can be probably confused by the class 8. So I will guess that it will oscillate a bit, maybe. My guess was wrong. It's pretty stable on pattern 3. But we can also provide more noisy classes, like this one. Noisy input, sorry. This should be classified as 5, but actually it looks maybe like an 8 or maybe like a 6. It's a very noisy pattern. So you will see the classification is not very confident. It's changing the mind every time. At the end, it guessed the 5, but it was changing every time. We can also have a number 3, but this one is also very similar to class 2, maybe. So we will see this. Or similar to class 7. Yeah, it's being confused between 3, 7, and 2. Okay. This is the standard way, the bottom-up approach to classification. But my goal was to show you that this is a generative model. We can go on the other way. We can use the top-down connections. And we can, for example, ask the network, well, I want you to generate a good-looking number 6. So we start with this layer clamped. And we ask the network to go down to the sensory layer. This is like the active brain perspective I was discussing before. Okay? So you cannot do this with a feed-forward backpropagation network. With a backpropagation network, you can start with the input and ask the output. But with a generative model, you can also start from the class and ask to generate the input. How will it look like? You see it's starting to generate something on the visible layer. So it's like if the network is thinking about the shape of a digit of class 6. And of course it's stochastic, so the shape is always changing. I can ask to generate okay, maybe a pattern from class 0. You see at the beginning it's completely noisy, but then after sampling, it's converging to a good shape of a pattern 0. Okay. Not always good. It's exploring the space of the possible configurations and is settling down to the most stable one. Okay. So I think this is a good example of how generative models, unsupervised networks, are different from supervised networks. With supervised, you can only classify. Here you can also generate the input distribution.
Alberto,
excuse me. Yes?
Go back, just to clarify how the learning proceeds. When you said you pick the class tree,
yeah,
and you use it, the noisy, for example, as an input, is this tree fixed and you keep it there, so this handwritten tree is still constant and the network iterates, or you pick this class and you're feeding the network with many examples from this noisy class?
You can do both. So you can start with only top-down class information and let the input to be completely generated top-down every time you sample it again. Or you can also combine. So you can generate a number 3 and leave it there and be like the new evidence for constraining the generation process. Okay. So you can do both.
When you said the classification is converging and then most of the time it was successful.
Oh, for the bottom up, okay. Okay.
The tree below.
That is fixed. Yeah, that is the evidence we want to classify. Okay. Yeah, yeah. In principle.
And the network was pre-trained.
Yeah.
So you're just using the network.
Exactly. Yeah, yeah, sure.
It was pre-trained, so
yeah.
that is not part of the training.
Yeah, no, sorry. Okay, that was a trained network. Okay. Yeah, we were testing the network.
And one thing that I would be concerned about is. Now, can you visualize better?
Yeah, I'll try.
You can try. So let's say that I have a trained network for the 10 digits, okay?
Let me try to exit.
No, okay.
I open it again.
No problem. You have a trained network for 10 digits, and then all in a sudden, you get a B, like a letter.
Yeah.
So what are the features that and you're still using this network for a letter, which is not part of the digit that you had in the training set. And I would like to know what's going on there.
Yeah. So let me see.
So what is, of course, if you ask the network to generate, the network will take the B letter and will generate something, probably will confuse it with an 8
Yeah,
or something.
yeah, exactly.
But what would be the quality of the feature that will be generated? Because then what I have in mind in terms of engineering problem is I can train the network and then I have a basic structure for a problem domain where I have a number of classes, a number of problems, and then all of a sudden I have a new class appearing.
Yeah.
And I would like to catch that one.
Yeah.
So I would like this network to be able to say, to start features that are relevant, or at least that those features should be telling me this is something that I don't know.
Yeah, good question and very good point, because one of the important features of these networks is that they allow for transfer learning. So you learn knowledge from one domain, like digits, and then you can use the features to represent letters or other type of handwritten things. But of course, the more specific the representation will become. For example, we have seen that here some neurons only fires for the digits number 7. That will not be used for representing something completely different. Maybe you can use the neuron firing for the 0 for representing the letter O, because they are basically the same. But if the patterns are very different, then the more specific the neurons will be, the harder will be to generalize to represent other type of structures. But what is important is that the lower levels, instead, are not domain specific. So these neurons are just detecting edges, crosses, borders, and they can be used immediately for representing letters or other types of patterns. So you can do some transfer of knowledge between different domains, but then if you become too much specialized at the top layers, you have to retrain or to maybe adjust to the new patterns that are coming from another domain. And of course, if you show maybe similar letters or digits, it's okay. But if I show you maybe a Chinese character, that is going to be very hard to process from the network. So there's always a trade-off between how much you want the network to become specific or general to process every type of patterns.
So in engineering, most of the time we have a domain area, and we know 99% of what there is there, but sometimes something strange happens. And we don't want the system to break down just because we haven't seen that.
Yeah.
We don't know anything about it. So with the Chinese character, we would like to at least the network tell us, this is a new cluster, I don't know how to treat it, but please, human being, come in and
help me figuring out. So I think that what is good about neural networks is that they are graded systems. So if you show something unexpected, they are not just blowing up. They are going to probably mapping to the space to the closest representation in the space they know. So they are trying to take the Chinese character and some way assign it to the closest pattern. But they will not assign it in the same way they assign the other digit. So you can see that the network is like reacting some way differently. So I think in principle they can represent a good trade-off because they can process the pattern, they will not break up, and they will try to map it in the closest space. But of course, you will see that the network is going into a different minima than it's usually going to. So in principle, maybe you can do something. For example, I've been training a network on Arabic letters and digits, and then I used it to classify Latin digits. And it was doing pretty well, like 90% of accuracy of classification, which is not the state of the art, but also not bad, considering that the network never saw Latin digits, okay, but only Arabic digits. So they can do some transferring of knowledge. And in the example that I'm showing you later, I will show you something even more interesting about the transfer and recycling. If I can go back to my presentation. Just to briefly mention that Google has been doing something fancy using the top-down effects I've been just describing. With the Google Deep Dream, you can take a picture, an input picture, for example, of people playing cards, and you fix a high-level feature, like I was fixing the class 0, and I was asking the network to generate 0, right? Now you can fix like the dog feature, and you provide an image with people playing cards, and you ask the network to some way find an equilibrium in the middle, and the network, for example, will replace the faces of the humans with dog faces. So it will learn to combine features and producing novel like hallucinations of images. So this is the typical fancy application that is very highly cited by the public and is boosting the popularity of deep learning. I don't know if it has a scientific relevance, but it's fancy stuff and people like it. Okay. Last thing that I didn't mention, it's about implementation of these algorithms. You can implement them on parallel hardware because neural networks are inherently parallel. So you don't have to engineer like locking of resources when you do parallel computing. You have always concurrent access to the same resources. Here, every neuron is independent from the others. Okay? So you can really distribute the computation on parallel hardware. For example, on graphic processing units. And we've been parallelizing some codes that you will be downloading later. And we had a speed up that was incredible compared even to a computer cluster. Like we were training the network in 15 minutes rather than 5 hours that were required in the computer cluster. And the parallelization was extremely easy. So in 1 month of work, I've been able to parallelize the whole code. Of course, Google then can use supercomputers. So it was able to train a deep neural network with 10 hidden layers, very deep network, with a lot of neurons and even more synaptic connections. And the training data set was just huge. It was frames extracting from YouTube videos, and it takes 3 days of intensive learning on Google supercomputers to train this whole hierarchy of processing. But still, this was completely unsupervised. Okay, so you see bidirectional connections, and some neurons became selective for extremely high-level concepts like faces or pictures of cats. So like I was showing you before, the neurons sensitive to the shape of the digit 0 or the digit 7, now we have a much higher variety of input here because in YouTube we have all the type of inputs. And some neurons are becoming sensitive to very complex concepts, even if learning was unsupervised. What does it mean? It means that in most of the YouTube videos, we have either faces or cats, which is partially true. And the network is able to discover these latent features of the data. Say, okay, if I have to describe the distribution, the statistical distribution of the pixels of images of your YouTube videos, I should grasp the concept of face, I should grasp the concept of cat. If we ask which are the preferred input to this neuron, you will see something like this. So these are the 48 most preferred stimuli for this neuron. Okay, you see they are all faces. So every time one of these inputs is presented to the network, this neuron is firing. It's saying, hey, there's a face. Hey, there's a face. So it acts like a feature detector for faces. Of course, sometimes it acts also if you have a ball, because the shape is very similar to a face. But I think this is a very interesting way to represent information at a high level. Also, let me just briefly say that supervised deep learning is still much more popular than unsupervised. This paper, 2012, has 12,000 citations. It's like impressive. How can they do it? All the giants of information technology are using these extremely deep architectures to classify, for example, images or pictures or faces or whatever, because they have a lot of supervised information. So they pay people to attach labels to all the pictures they have, so they can build extremely big data sets that can be used to train networks in a supervised way. So this is the popular trend at the moment. We, in cognitive neuroscience, don't like it because we don't think this is the way humans learn. But if you have a lot of supervised labels on all your data, then you should go with supervised networks like Google is doing, and you achieve very impressive performances. Okay, so for example, in machine vision, these type of models can really give a class to different types of images with high confidence. Okay, here it was even able to say that this was a leopard, and maybe with less confidence a jaguar, and maybe with even less confidence a cheetah, which are all very similar, but the network was able to pick up the exact class from the image. They can also do like detection of objects. They can put bounding boxes and also classify them with a high level of confidence. Or they can do segmentation. This is very used for self-driving cars. So you have a camera on top of your car, and the deep neural network is trying to segment the images. So it's saying, oh, there's a street here, car here, building, tree. Say that there's a person here. It was just the shadow of a bike. So sometimes these algorithms can also fail. But of course, they still need to be improved. They can do language processing. State-of-the-art speech recognition is achieved using these type of models. The Siri assistant on your mobile phone is based on deep learning. They can also do language translation, real time. You take a picture of some written language, and it automatically translates in different languages. And there are many, many other useful, successful applications of deep learning. They can do document retrieval, medical screening. They can even play board games or Atari video games. This is when they are combined with reinforcement learning. But I don't want to discuss this huge amount of applications. Rather, I want to show you an application to cognitive modeling that I've been working on, which is related to the transfer learning question that Michele was asking. So we have been exploring this simple architecture. There was one restricted Boltzmann machine trained in an unsupervised way, so generative learning, on a big set of natural image patches. So there were different subjects, like the Yosemite Park you see here. We derived small patches of 40 by 40 pixels. They look like these. Okay. And we trained a neural network to generate this type of visual input. We also performed a simple whitening on the images, but this is just a detail. After learning, these neurons were able to extract basic visual features like this. So like edges, gratings, principal components, shadows, color gradients, gray scale gradients. So what does it mean? It means that these type of features are useful for compactly represent this type of input. Okay. Up to here, it was pretty straightforward. It's an interesting result, but this was expected. Okay. But then what we've been doing, the progressive development of these receptive fields. So you see at the beginning they are completely random, but during learning they become more and more specialized to some type of features. Okay. So this is how the network is progressing with experience. Each square is a different hidden neuron, and each hidden neuron is picking up a different feature from the input training data set. Okay. But at the end, we recycled this knowledge learned during the first stage on the natural images to also learn printed letters like this. So this was something that the network was not able to process before. We stacked another layer, another Boltzmann machine, and we performed unsupervised learning on a large data set of letters. Of course, not just 26 letters. It was like 50,000 different letters printed in different styles, different fonts, different sizes, different displacement in the visual field, and so on. The aim was to recycle this basic architecture, this basic knowledge, which was extracting from just looking at natural scenes, and use it for bootstrapping, learning also on more complex patterns like letters. This is in line with the theory that orthographic processing in the brain does not start from scratch. When a baby is learning to read, for example, his visual system is not random. It's not like randomly connected like you do with neural networks. But rather, the primary visual cortex or the early stages of the visual processing have been already shaped by experience. So when the kid is being born, during the first 3-4 years, he is looking around to the garden, to the trees, to faces, to all this type of rich stimuli. And he is building knowledge in his primary and also, of course, higher order knowledge in the secondary and associative cortex. Then when the kid wants to learn letters, he can start from these high-level features in the primary visual cortex in order to learn letters, which indeed have been shown to be processed by these two cortical areas. So this way we were able to show that natural images can be recycled to more easily learn also other type of patterns like printed letters. And the receptive fields of the neurons here looked like this. So you see from the basic visual features, you can build more complex features which are domain specific for the letters. And the network was able to recognize letter with a very high amount of noise. So we presented noisy stimuli, and the network was still able to recognize them at 50% of accuracy. And importantly, the readout accuracy was improving as we moved up in the hierarchy. So from the early visual stages in the thalamus, then to the primary visual areas, then to the secondary visual areas, the performance was increasing. So this is the noise level added to the stimuli, and this is the accuracy. And you see that the best accuracy is achieved by the deepest layer of the network. And this is interesting for psychologists. We can simulate. Yes, sorry?
I would be interested in knowing having another cube.
Yeah.
With a full stack, just train on the letter.
We do, of course. Reviewers asked this.
Where is it?
It's in the paper.
Okay.
It's in the middle between the orange and the other ones.
So you're telling me that you do better with this approach?
Yeah. This is why we published it in Nature Human Behavior. Yeah. Because it demonstrates that recycling is benefits for learning also things that usually when you train neural networks, you immediately start from the patterns of your domain. We say, oh, maybe do a step back. Do unsupervised to gain knowledge before, and then you can start from a privileged standpoint to learn also other types of features or more domain-specific knowledge. So we were also kind of surprised that a network trained directly on the letters was having a performance dropping down much more faster. One also possible explanation is that it's more prone to overfitting because you don't have enough variability maybe in your training data set. So it's picking up too much specific features. Instead, with a huge amount of natural images, you are reducing the overfitting of the model. So it makes sense at the end, I think. We were able, for example, to simulate the same type of confusion errors produced by humans. So when you ask in a psychology lab to discriminate between two letters, maybe under noisy condition like this, you will likely confuse, for example, the O with the Q because they share many features, while the O is very different from the I or from the T, so you can easily discriminate them. If two letters are similar, like O and Q, the confusion matrix will emphasize it, okay? Or maybe the N and the M. Now it's not very clear from this picture, but basically the network confusions were extremely similar to the confusions made by human observers. Yes, please.
Do you have a similar plot for the performance with distortion instead of noise, like distortion?
Oh, we don't, and the reason is that with humans they don't test with distortions, so it will be interesting. But our goal was to compare with data on humans, and humans usually are tested by only adding this type of noise. I guess it will work pretty well also with distortions, but in that case, if you want to have a state-of-the-art accuracy, you should train also with distorted patterns. to have it more stable and robust against this type of manipulations of the input. Or also you can build a hierarchy of like a dendrogram to measure similarity of the letters using the internal representations of the network. So you see for the network, Q and O are highly similar, and they are also quite similar to C and G. They form a cluster. Same for E and F, or for P and B, they form a cluster. And this type of dendrogram is pretty much similar to the dendrogram that you can build based on human similarity ratings. So also in this case, the network was fairly similar to human behavior. Then what you can do, go to another model. We want to learn sequential information. So up to now, we have been concerned by static input, like a letter, a digit, an image, a face, images, static images. But maybe sometimes we have a dynamic input. So we have a sequence of images which are highly correlated in time. I guess in the engineering and telecommunication literature, this is what usually happens. You have streams. You don't have isolated data. Okay. So how to learn this type of data? We need to use another set of connections, you see. I call them HH because VH stands for visible to hidden. Now we have hidden to hidden. These are recurrent connections which are delayed. This is why I put an arrow. It means, we will see in a while, that the model is maintaining its internal state, which is used like a hidden Markov model to process the subsequent information. And after learning, we can sample from the model. We ask the model to generate an input. You see, it's not really Newtonian dynamics. It's more Brownian dynamics, which means that the model is not really able to capture the exact physics of these bouncing balls. But still it's doing quite a good job because it's able to say that there are 3 different objects. They are never overlapping. They are bouncing. So it's a fairly good generative model of the input, but still research needs to be done to improve the model because it's not able to closely mimic the Newtonian dynamics embedded here. Okay. Just a few words on the representational power of these sequential models. One might ask, I can just use a hidden Markov model, right? Well, hidden Markov models, they use a localistic representation of information. We have k possible states. We can represent k different states in the system. Imagine that states are binary, okay, for simplicity. So, for example, 20 hidden states. The system can only be in 20 different states internally. But distributed state models, like neural networks, can use exponentially more hidden states because each state corresponds to the combination of the activation of hidden units. So if we have 20 hidden units, for example, we can represent 2 to the power of 20 possible states. Okay? So it is combinatorial, the representation. It's not localistic. This is why they are much more powerful. They can represent much more heterogeneous distributions. This is in case of binary neurons. We can also have real-valued neurons. So how does it work in the recurrent temporal restricted Boltzmann machine? That's a long acronym. During inference, we observe some evidence in the visible layer. Okay. This is how time goes from left to right. We use the visible to hidden connections to infer the state of the hidden units. And we can also use an initial bias, like the initial state bias. Okay. So this is like the probability of the hidden units given the visible units, okay, at time step 1. This is like a simple restricted Boltzmann machine. We are inferring the hypothesis given the evidence, 1 step. Then we see another element of the sequence, but this is not independent from this one. They are correlated. So we infer the new value of the hidden units by also taking into account, beside the current evidence, the previous hidden unit activation. So these HH connections, you see, it's the recurrent connection I printed before in the graph. So this is like a dynamic bias, which is adjusting the activation of these hidden units. So this way, the new internal representation is not only dependent on V2, but it is also dependent on the previous activation of the hidden units, and so on until we process the whole sequence. Okay? So this way, the final representation of the sequence will take into account all the history of this input stream. Okay? We can also generate from these models. So in order to do sampling, what we do, we start from an initial state, and we use the visible to hidden connections to generate the first element of the sequence. Then we keep it fixed, and we infer the value of the hidden units, and then we sample from the model top down, and we infer the value of the second element of the sequence, which is now conditioned on the context, on what we have been generating before. And we do it until we generate a whole sequence. Okay? So you see, we can generate sequences of correlated elements taking into account the history of what we have been generating before in this way. Okay? So this is how restricted Boltzmann machines can be extended on time to process sequential input. And have been using these models to model the structure of letter sequences in English. So English monosyllables can be existent, like proof, tea, whole. These are English words. They can be well-formed, but not existent. We call them pseudo-words. Gruding, keen, they sound good, but they don't have a meaning. They are not English words. Or they can be ill-formed. I cannot pronounce these because they are just random sequences of letters. So we are interested in discovering the structure of these two classes by starting only from existing English words. I trained a network with many English words, and then I asked the network to generate words. Or first, actually, I asked the network to predict the letter following a certain context. It's like when you type on Google, search something, it's using what you are typing to predict the future. This is doing the same. It's doing inference on what's going to happen based on the history, on the context. Okay. But also, I can sample from the model. So the model was able to generate a lot of good-looking pseudo-words. None of these are English words. Armed, dog, hind, perch, tint, brow. But I can pronounce them because they are following the English phonotactic structure. Okay. Or we can even generate music with this type of models. We provide to the input, as input to the network, polyphonic sequences of music. The network is trying to understand the hidden structure, the transition probabilities between the elements of the sequence. And then we can ask the network to generate the music. Now I need speakers again. Sorry. So this is a sample of a training sequence. Oh. So pretty easy structure, but still interesting. Another type of sequence. So it is polyphonic music, which means that we have to generate many notes at the same time step, which should be in harmony, and then they should be correlated on time also. So it's a pretty challenging task. Now, of course, it's not Beethoven, but the harmony is there. So it's not generating strange patterns. And also the temporal structure is putting pauses, is trying to set up a rhythm. So it's not too bad. Sometimes it starts with a good whoop. Try to skip. is already doing some improvisation. And in a while, you will hear something that is more similar to Stanley Kubrick movies, you see, because it's producing a drift in the distribution. When it starts to make errors, then the errors are propagating. So it's like more a horror movie. Yeah, Stanley Kubrick will pay for this, I guess. Okay, I stop here. So this was just to show that they are not restricted to applications to language or images or text, but also to other interesting tasks like predicting music. But also not only to simulate human-like abilities. Also music is something produced by humans. But in a more recent project, we have been exploring these models to optimize, for example, telecommunication systems. And I'm sure you are more interested in this application, but it's going to be only 2 slides. I'm sorry. But if you have further questions, we can discuss them. So the basic idea of the Kobanet project was to use this type of deep learning methods to optimize, in general various aspects of telecommunication systems. And this is in collaboration with the Department of Information and Electrical Engineering at Padova University. So we have been using a variety of both unsupervised and supervised algorithms. Reinforcement learning is still missing. I think it's very relevant for telecommunications, so maybe in the future we should explore also that. And we try to combine them to optimize different network parameters, like transmission rates or other type of protocol parameters. The final goal is to optimally allocate resources in a smart way. So you know better than me that cognitive radios are trying to optimize the telecommunication process in a way that is superhuman, because maybe humans cannot really engineer precisely the system functioning, but maybe by using learning techniques, we can improve on this type of optimization. So there's a paper if you want to read more about the details, but the basic examples that we have been investigating is these ones. So we have several clients, maybe mobile clients or other type of internet clients, which are connected, but there's a bottleneck in the resource delivery, and they're asking multimedia content like videos. Okay, and in the media server, there's a cognitive engine which is trying to understand what's going on in the communication channel in order to optimize the data that is being delivered. Okay. More in detail, in the media server, the videos are encoded with the H.264 format at different quality rates. Okay, so we have a video which is in high quality and different versions of the same video until we reach a minimum quality. Okay, and the idea is that based on network congestion and also on the user requirement, we can decide in an optimal way which video to deliver, which quality of the video to deliver. Okay. But most importantly, we wanted to do this by estimating the quality of the video directly from the raw data, which means from the frame size of the video. So when a user is asking for a video or is uploading a video, we are just looking inside the frame sizes transmitted along the channel. We are not really processing the video clip, which is a computationally demanding task. But we are just looking at the frame sizes, and based on the frame sizes, we are trying to estimate if the video, for example, is dynamic, requires a lot of data to be sent, or maybe the video is static, so you can really send a few bits of information, or you can send a low quality compressed video, and so you save communication resources. And we were able to do some video classification and quality rate estimation tasks by really starting from frame sizes. And this was made possible by training restricted Boltzmann machines on a data set of different videos encoded only in terms of frame sizes. So I think this is a simple application, but it's just to show, to demonstrate that you don't need necessarily to model human cognition, like recognition of visual scenes, of movies, of music. You can also try to model something that is more machine generated, like the traffic flow of digital information. Yes?
Another question. This is very good. However, generalization, what you shown before with the music, although I like it, in terms of telecommunication network, control network for a factory system, probably is a problem.
Yeah.
Because for the video, the end user will not be able to see anything decent, maybe this is not, but if you're controlling a system in a factory control automation setting, it would be maybe very dangerous that you are deviating from a good control strategy, or even that you're screwing it up. You can break the machine. And so I'm wondering about the generalization capabilities of these things, or whether there is a way to maybe use this and detect whenever this is not providing a good answer. So you can basically fix it through another process that is maybe not elegant, but...
So, good question. I like that Michele is stressing on this point, because, well, we were testing the generalization capabilities by testing the model on new videos that were never shown during the training phase. So the performance was evaluated on a separate test set of videos, new videos. And we also tested different type of compression. We tested H.264, but we also tested HD videos, HD videos, different encoding formats. But still, if you have something really unexpected, the model will try to map it into something that he is used to process. So this is, I guess, the biggest obstacle why engineering is not yet fully exploiting this approach. Because this approach is probabilistic, is fuzzy, we cannot control these systems. We are not guaranteed that the system is always working. And if you are providing an engineering system, something that must work, must be fault tolerant, then using probabilistic methods like these, or that we don't really understand, is still problematic. So this is, I think, something that we must look in the future, how to be fault tolerant when these machines are getting the wrong...
This is exactly the problem I have every time I try to use these things. How I solve it so far is very problem specific. So you look at your problem and you need to come up with some theory and some probably analytical tool that allow you to at least understand whenever the solution that you're getting is within some boundaries, some constraints that are feasible or good enough for you. So then, this is what I'm doing. Basically, when I build an architecture like that, I want this fallback check. So the decision maker, before implementing the decision made by this neural engine, is going to assess whether this is within the boundaries. And if it is not, maybe I'm using some heuristic approach that is... I know this is not optimal, but
but it's a way to have it working almost safely.
This is how I'm dealing with that.
Okay. Yes, please.
I see this block that is called quality rate estimator.
Yeah.
So you are estimating the user experience.
Yeah.
This kind of thing.
Yeah.
And you may want to use this information maybe to feedback the video encoder to change the...
So the way we estimate
so you can kind of reinforce...
That's a possible approach, I think. The way we were estimating the quality rate was by looking at how the curves degrades when you compress the information. So it was mostly based on... We were fitting some polynomial curves, and we were trying to predict the coefficients of the polynomials to have like a raw coarse estimation of the quality rate. But having a user giving you a feedback is going to be like a good way to have a supervision or a reinforcement signal that can further improve the model. Yeah, that's a good observation.
So this kind of deep reinforcement learning can be really useful for...
Indeed, in the original proposal, which was submitted for an ERC grant, but unfortunately we didn't get it, the full architecture also provided a reinforcement learning module. So in order to have like a more direct feedback about what's happening in the system as a whole, and asking also the users to provide additional feedback. Just to say again something about the fault tolerance of these models, I think Michele is right in pointing out that if we have engineering applications, we cannot just say, oh, it's drifting, it's generating the wrong type of music, I laugh about it. No, it's really dangerous to have a system like this working in practice. But also, we should note that, for example, the Google cars, the self-automatic driving systems of Google, are being based heavily on this approach. So it's going to be risky that we have self-driving cars based on learning. So the car is learning by experience, of course, with the assistance of a pilot during the extended training period. But then when we will have the car free on the street, still maybe something unexpected is happening. Maybe a solar eclipse, which changes all the lighting conditions, and the car can just go and crash. So if we really want to apply these methods, we must be prepared that they might fail, like human fails also sometimes. So a possible solution, other than providing heuristic and B plans if something is going wrong, would be to train these models on the largest range of situations we can imagine, which is going to be very challenging because you need a lot of data, a lot of different scenarios. But for example, the Google cars are being trained in all the possible streets, street conditions, lighting conditions, big cities, small cities, things running in the middle. So if you provide a lot of experience to the algorithm, he will also be able to more flexibly adapt to the changing conditions of the environment. If you only train the system on some particular type of streets, then you go inside the city, the environment is going to be difficult and completely different from what you have been seeing during training, and the algorithm will fail. I don't know if this will also be easily to apply in the telecommunication setting. I think telecommunication is really a challenging domain for these algorithms. It shows some promise, but also a lot of things need to be fixed and investigated before we can really assign responsibility of these, to these automatic systems. Okay, so I'm almost done. In conclusion, my suggestion, when should we apply this type of models? Well, the first question is, do we have a lot of data, like thousands or even hundreds of thousands of samples to feed these models? If the answer is no, then please stick to other machine learning algorithms, like support vector machines or kernel methods. They are very robust, even with few training data. This should be the primary choice if we don't have a lot of data. If we do have a lot of data, these algorithms like support vector machines might have problems because they don't easily scale with big problems. So maybe yes, we should use this type of neural networks. If we have discrete classes or real valued predictions like in regression, which means we have labels for the examples, then we should use supervised models like error backpropagation networks. If we don't have labels, then this is where we should use unsupervised models, like those based on contrastive divergence or restricted Boltzmann machines. But in any case, if we guess that the data have a hierarchical structure, then we should apply multi-layer models. So we should try to build a hierarchy of representations, like in deep learning, because this is going to build more abstract and more high-level features that are more useful to solve the task. Of course, it's not easy to understand if your data has a hierarchical structure. Again, in the telecommunication settings, sometimes the data is just strings of bits. We don't really know what's inside. Once you encode things and you send them into a communication channel, it's much harder to tell which is the type of structure that I should be expecting. So usually a good approach is to start with a simple model, only one layer. Then you try to stack maybe 2 layers or 3 layers to see if the performance is improving. Okay.
Just a comment related to what you just said. There is one paper which will be coming out next year. We are reviewing it in Transactional Cognitive Networking. It's a new journal, Transaction. They are exactly doing this. So they take the standard modulation encoding channel, the modulator decoder, and they replace this chain. I mean, the channel is still a real channel, but they replace the transmitter and the receiver with neural networks, basically. So they train it in a supervised manner, and then they explore different architecture, and they are getting state-of-the-art performance sometimes a little bit worse than what we can get with some state-of-the-art MIMO and very aggressive coding, but not too bad. So that is, I would say, next year, some papers will come out on this, and the suggestion that, because we are reviewing this paper now, and what I see is that although maybe we are not yet state-of-the-art, they are promising.
Yeah.
So even in the bitstream, we can do something. And the second suggestion is, in a telecommunication network, there is a lot of modeling going on. So I wouldn't recommend to apply blindly these things as you do for images. So images, you have a bunch of pixels, and you build a pixel matrix, and you put it as input of then your network. In a telecommunication network, you can exploit the fact that you are really knowledgeable. I mean, the engineer or the scientist behind it has a very profound knowledge of the problem at stake.
Yeah.
So you should be really creating input vectors that are already meaningful. They are not features yet, but they are already meaningful. So instead of going straight to a representation, I put every bit I have, and I don't even know what I'm putting in the input of the network. There is this step here from the problem definition to the actual input of the network.
Yeah.
And this is very important.
Yeah. You have expert knowledge that you can exploit to provide better representations to the input of the network. Yes, thanks. Okay, almost at the end, also the limitations of these algorithms. Of course, they have many, but the one that I find more daunting is that we have a lot of hyperparameters. What does it mean? We have to establish which is the best learning rate, how many hidden units, how many hidden layers, many other like momentum, weight decay. There are regularizers for improving learning, or sparsity constraints, or how long should the learning be. These are all hyperparameters related to the problems of nonlinear optimization, related to overfitting, model complexity, and we don't have a principled way to set them. We don't have analytical reasons why we should prefer one learning rate over another. Yes, we have some heuristics, but still when I train my algorithms, I try maybe 1,000 different networks. I do a big for loop, and I explore with a grid search the best parameters, which is very, very time consuming. So this is why you cannot go one shot with these algorithms. You need a lot of exploration. So this is something I guess, and I hope will be improved in the future. How to learn control policies. This is related to the reinforcement learning and to the discovery of causal structure. This is something that in the last years have been showing some groundbreaking results, like the Google DeepMind team is coupling deep learning with reinforcement learning algorithms. And so this is a problem that I used to mention as an open question, but now they are providing good hints about how to combine with reinforcement learning. And finally, especially from an engineering perspective, how can we understand what the model is doing? It's just a black box that is optimizing something. Can we look inside the black box? In my field of investigation, I can go and measure, for example, the receptive fields of the neurons, or I can probe the network with different inputs and record the activation of the neurons. And then maybe I compare the response profiles of the neurons with the biological neurons. In the monkey brain, for example, or in the rats, they are recording with very tiny electrodes the activity of the neurons. And sometimes my models show behaviors similar to the ones recorded in vivo on animals, which is amazing. I can validate my models with some measures. Or I can look at the confusion errors made by the network and compare them with the confusions made by the humans. But for telecommunication, how can we go inside this black box optimization problem to understand if it is working properly, or just to understand how the network is solving the task? I think we need more analytical methods here also. So in conclusion, I said I hope I convinced you that artificial neural networks are powerful tools, both for engineering intelligent systems, but also to better understand the human mind and the human brain. There are many different types of artificial neural networks. They share some basic features, like they use simple processing units, neurons, that cooperate to produce complex behavior. The connection weights of the network are the parameters of the model that must be learned, and they can be adjusted, for example, by optimizing a cost function. Okay? This is the basic ideas in neural networks. But there are also critical differences among different types of network architectures. The architecture defines the computational properties of the network. If we put a bidirectional or a feed-forward or a recurrent edge in the architecture, this completely changes the behavior of the network. Some architectures, they incorporate feedback connections and they implement unsupervised learning, and we like them as cognitive neuroscientists. In particular, Boltzmann machines can be interpreted as a type of probabilistic graphical models, namely Markov networks. So they can be coupled with the extensive literature on Bayesian statistics, on statistical mechanics. And they can also be combined in order to learn hierarchical models, which we call unsupervised deep learning models. They can be also extended to process sequential information, and they can be applied to a wide range of problems, going from music perception to telecommunication optimization. I list some references. These are some papers that can be useful. They are probably in order of importance. There's a very good Nature review on deep learning, which is anyway focused on supervised deep learning. So you will see in the last paragraph, the authors, which are three of the most prominent scientists in the neural network community, they say, oh, we just focused on supervised deep learning, but keep in mind that probably unsupervised is even more interesting. So it's good to note. Yes, please.
Yeah, the new book from Benjo, how would you recommend that one? Yeah. How you see this one? Can you spend a few words?
I think this is going to be the definitive Bible for deep learning. So if you're really interested in exploring all the different approaches to deep learning, this is where you should go. And there's a first part, which is like an introduction, which is algebra and probability theory, some mathematical background. Then the second part, which is the most consistent, is on supervised deep learning, so convolutional neural networks, backpropagation, these type of topics that I didn't discuss here. And the third part that is listed as research frontiers is about unsupervised representation learning. So this is a comprehensive source. It has everything I warmly suggest it. So yeah.
Also, it is written for engineers, so it is
not
a tremendous amount of math. I mean, I found it very
Yeah. I think really it will become a reference. And also the interesting thing is that it's freely available online. So you can download the PDFs or looking it from the browser. So I really think this is very interesting resource. And I thank the authors for sharing this important information. Okay, so thanks. We will finish in now 5 minutes breaks, and then 20 minutes of hands-on practice, so if you have your PC. Otherwise, you can just look at the monitor, and I will try to do it with my own laptop. So let's take a little break and go on for the last part. Thanks.